Good morning. Today we discuss about this resolving power, focal length, angular aperture and depth of focus. Myself, Professor Kamthana DC from the Department of Microbiology, Shri Guru Buddhi Swami College, Purna. We first see what is resolving power. Resolving power is the ability of lens system to distinguish two adjacent points of the lines as distinct or separate. We can take one example, that is human eye having the resolving power of 0.2 millimeter. It means that the points are the lines which are having the distance in between them as 0.2 millimeter. This can be seen as separate dots or the lines, and if these are closer than 0.2 millimeter, these appear as a single line or a single dot. It depends upon the two factors. Number one, wavelength of the light used and the numerical aperture. This is the formula, that is resolving power is equal to wavelength divided by 2 into numerical aperture. First, it is the wavelength of the light used. If wavelength of the light, if it is less, then it is giving the more resolution and vice versa. The second factor, it is depending upon the maximum light admitting power of this lens system, and which is again related to the numerical aperture. This numerical aperture, it is again related to this angular aperture. The next terminology we see, that is the focal length. This is the convex lens, and through this lens the light rays are passing, and after this passing through this convex lens, these emerge and cross across a point, and this is called as the focal point. The distance between the optical axis of the lens and the point at which these rays cross, this is called as the focal length. And these are the parallel rays, and we can define it as a parallel rays of light go through a convex lens. They emerge out and cross at a point. This point, it is called as the focal point, and the distance between the optical center of the lens and the focal point, it is called as the focal length. When the object it is outside the focal point of the lens, the image formed is real and inverted, and when the object is inside the focal point of the lens, the image formed is virtual and erect. When the object it is closer than the focal point, the magnification it is more, and if the object it is far away from this focal point, the magnification it is less one. Then we see what is angular aperture. This is the angular aperture, and this half of this angular aperture, it is called as the theta, and this is half of this angular aperture. This angular aperture, it is the cone of most divergent rays of light coming from the condenser and passing through the object. This object emerge the light rays, and these light rays out this inverted cone of light coming from this condenser passing through the object and coming to this objective lens, it is called as this angular aperture. Now we see the depth of the focus. This also called as the depth of sharpness or the penetration, and it depends upon the numerical aperture and magnification, and there is inverse relation between the depth of the focus and numerical aperture, depth of focus and the magnification. If the depth of focus it is more, then this numerical aperture and the magnification, these are less one, and if this depth of focus it is low, the numerical aperture and magnification it is high one. Therefore, we must take care while adjusting the high power objectives and this low power objectives. The high power objective, these are having the low depth of focus, and these low power objectives, these are having high depth of focus. Thank you for your listening.